Hi everyone, welcome to the lecture on independent events. This is video number 3. We're talking about independence of more than 2 events. Okay, let's look at this example. Let's say there are 3 coins that are tossed and we have 3 events. Event 1 is A1, coins 1 and 2 match. A2, coins 2 and 3 match. And A3, coins 1 and 3 match. Okay. Let me write down the sample space just to make sure and the probability of each outcome. Right, so I'll write the outcomes here and then the probability of each one. And essentially I'm getting this as an output of the outcome tree method, right? So you can start from the beginning and use that method. I already have the outcomes. So either we get heads, 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 right? Or heads, heads, tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and all tails. All right, so we already knew that, but I just wanted to enumerate that. And I know that again, from the outcome tree method, every time you'll have the first coin, heads or tails, and then the second coin, heads or tails, and so on. So the probability of each outcome using the outcome tree method is 1/8 for each of them. So I'm not writing all of that, it's all 1/8. Okay, so now if I ask you to find the probability of A1, right, which is coins 1 and 2 match, which means a case like this, or this, or this, or this, right? So there are 4 cases that I figured, right? So the probability of A1 is 4 out of 8, which is 1/2. And this is equal to, by the way, the probability of A2 and A3. You should go ahead and double check that, right? So for all these events, probability of A1, probability of A2, and A3 are equal, right? Now let's look at the probability of A1 and A2. Okay, that means all 3 match, right? So how many in all 3 match? Just 2 of them, right? All heads and all tails. So 2 out of 8, which is 1/4. Now, if we look at independence for these 2 events out of the 3 events that we have, we can see that A1 and A2 are independent because probability of A1 and A2 is equal to the probability of A1 times the probability of A2, right? However, these events are not independent together when we look at them, all 3 of them, which means probability of A1 and A2 and A3 is not equal to probability of A1, probability of A2, and probability of A3. How do I know that? We can figure this out. So this is probability of A1, A2, A3. So again, 1 and 2 match, 2 and 3 match, 3 and 1 match. That means all of them match. So this is 2 out of 8, right, which is 1/4. But what about the probability of these? We know that each of them has a probability 1/2, 1/2, 1/2. So this is 1/8. Right, so obviously this is not equal. So here something called k-way independent event comes into picture. For example, for our example, this is a 2-way independent event, right? It's 2-way independent event. Why? Because it is independent for each of the 2 events, but it's not independent for all 3 of them. So similarly, for larger number of events, we can have k-way independence, which means probability of any k-way intersection is going to be the product of the k individual event probabilities, right? But it's not essentially going to be for all the events. For example, let me write down probability of any k-way, which in our example was 2-way, right? Intersection is the product of the k individual event probabilities, right? So it's not necessary that the events are going to be independent for all the set of events that are available for that experiment, but there could be a k-way intersection of events that's independent. And this is called independence of more than two events. Now, in the next video, we'll look at a very interesting problem called the birthday problem that will further help us understand independence.